Hi, I'm Justin. I'm an undergraduate room leader for Dr. Schaefer. If you need anything, email me, and I also have office hours. This is a review for your exam 2, Bio 282. Let's get started. Oh, about me, I guess. I'm 20. I'm a bio major. I'm a junior. All right. So the double stars indicate something that I think is really important to know, whereas the info within these brackets over here indicates something that I included just for clarity or to help with any explanation that might be wanted, but you should not commit your time to memorizing it. We're going to do some bond review. We're going to talk about energetics, and then energetics really ties into cellular respiration and photosynthesis. I put timestamps in the description so you can skip around to wherever you might need to go. Bond review. An atom is the smallest unit of matter with unique chemical properties, and an atom is composed of 3 different things, or it can be. And these are called subatomic particles. You can have a proton, which is positively charged, and you can have a neutron, which is neutrally charged, doesn't have a charge. And both of these are in the nucleus, and then orbiting this nucleus are very small negatively charged particles called electrons. So all atoms have the central nucleus containing protons and or neutrons. Around it orbit or stick around in a way negatively charged electrons, which are attracted to the positive nucleus. Now, they don't actually collide and like stick together because of different weird subatomic physics properties, and that's really not needed. What I wanted you to take away from this is that almost everything occurs naturally and interacts with other stuff to achieve the most stable form.
Let's review skeletal structures. Lines are bonds with 2 parallel lines indicating a double bond. Bands and naked ends are carbons. What I mean by naked end is there's nothing attached over here, whereas this is also kind of looks like an end, but it is actually attached to oxygen. This is a bond going from the carbon to the oxygen. Carbon wants to make 4 bonds, and hydrogen wants to make 1 bond. Carbon always has 4 bonds. If it appears that only 3 or 2 are shown, the other 1 or 2 bonds are to implicitly that's redundant, are to implied hydrogens. So over here, we see that this carbon has 2 bonds going this way to this carbon, and 1 bond going this way to another carbon. We only have 3 bonds accounted for. We need a 4th one, and that one is to a hydrogen. For example, over here, there's a carbon, because it is an end. It is bonded to this carbon. It is bonded to this carbon. Only 2 bonds. We need 4 total. Our hydrogens are implied. When there are 2 elements next to each other, there's also a bond implied, such as this OH over here. While we don't draw that line going between them, there is a bond between that oxygen and that hydrogen.
So let's review bonds a little bit, specifically covalent bonds. So a covalent bond is where 2 atoms stick close to each other because they're sharing electrons. These electrons are negatively charged, and they're both stabilized and attracted to the positive nuclei, nuclei being the plural of nucleus. They interact to achieve the most stable form. So what you really want to know about this is that covalent bonds, which, with 2 electrons in them, they hold some amount of energy. That means the electrons themselves have energy. And if you can break this bond, you can utilize the energy within, because when you break it, you release energy to do stuff. The energy stored within these bonds is called chemical energy. Chemical energy is a form of potential energy, but at the bond level. So electronegativity is an atom's tendency to attract electrons. An atom with a low electronegativity will tend to have its electrons taken from it a lot, whereas a very electronegative atom will tend to take the electrons or hog electrons from another thing a lot more. And this has a couple of detrimental impacts on their properties. So when you're trying to identify an electronegative atom, I'm not even going to talk about this part because in the biological systems, you can get by with a shortcut. NOF. Nitrogen is electronegative, oxygen is electronegative, and fluorine are all very electronegative. So a polar covalent bond is one that involves an electronegative element which hogs electrons NOF along with a that is bonded to an element like carbon or hydrogen, which is not very electronegative. So this results in the electronegative atom hogging that electron, becoming more negative, and the victim getting a little more positive and becoming a little bit less negative. There are a couple of effects of this, and this is a pattern that you want to start thinking about. Because it's a polar bond, their bond length is short, like the distance between them. Because it's a short bond, that means that it's a strong bond, as like there's more stabilization forces close together, like negative, positive, and whatnot. So here are some examples: oxygen to whatever thing, nitrogen to whatever thing, fluorine to whatever thing, and so on. And here's a non-example, which would be O2. While oxygen is indeed part of our very electronegative trio, because it's to itself, it pulls equally, meaning that there is no unequal give of electrons, and it is actually very nonpolar. We're going to talk about nonpolar bonds. So this is a covalent bond where the electronegativity difference is small. So the electrons are more or less shared equally. For our purposes, we'll just say they're shared equally. But if you want to know more about it, you can read this little explanation over here. And compared to polar bonds, because they're shared equally, there's not really much hogging going on. You want to know these. Bond length is longer, and because it's a longer bond, it's weaker, which means that it's easier to break. So examples will be carbon-carbon, carbon-hydrogen, oxygen to oxygen. Compare them. So you have an electronegative element, you probably have a polar bond. Do you have just carbon and hydrogen, or do you have the same element? Then you have a nonpolar bond. Because it's a polar bond, what is our electronegativity difference? That means that we have a greater electronegativity difference. And because of that, we have a short bond length. Because we have a short bond length, we have greater strength in our bond. And because the bond is strong, it is difficult to break. Now, try and do the same thing for our nonpolar bond. Pause the video. All right, let's go over it. So for the nonpolar bond, our electronegativity difference is lower, smaller. Our bond length is longer, and our bond strength, because of that, is weaker. Because it's weaker, that means it's easier. That means that it is less difficult to break it. You might be asked to order, like, oh, like which one has the greatest chemical energy, which one has the strongest bond, whatnot. So we're going to go over this. A single bond versus double/triple bonds. A single bond is considerably longer / weaker than a double bond, if that makes sense. And then a double bond is considerably longer / weaker than a triple bond in order of increasing bond strength and decreasing bond length. Because the lower bond length, the stronger. We have our single bond, our single bonded carbon, our double bonded carbon, and then our triple bonded carbon. If you're tested on it, you shouldn't expect to compare C double bonded C to a C double bonded O. It would more like be comparing C double bond O to a C single bond O, which a C double bond O would be stronger. Let's move on to energy. Energy is something that is able to do work, where work is just some action that is being done. I mean, the study guide talks about it, but I really don't think you have to really know about it. But kinetic energy is the physical energy of motion, right? And then potential energy is a little more complicated, but it's stored energy. Like if you do something, then it can convert into kinetic energy and do something. So that could be like a I don't know, like this Rubik's cube, right? So it's on top of my head, and if you gave it a little bit of a nudge, it would fall off. So right now it has potential energy, right? Once I push it off, it'll convert into kinetic energy. We talked about this earlier, but I'm going to talk about it again. So chemical energy is the potential energy stored within bonds. Like with my Rubik's cube, right? Potential energy due to the force of gravity, and then but you give it a little nudge, right? You break that link. It's kind of weird, and then it gets converted into kinetic energy, which can actually do something. Sitting on top of my head wasn't doing anything, but falling down, it can hit my toe, and I can be really disappointed. If a bond can be broken, the energy within the bond or within the electrons can be converted from their chemical energy to do some kind of work. But the important part is if a bond can be broken, you can utilize the energy within. If you can't break it, the energy cannot be used. Strong, stable bonds have very little chemical energy, as it takes too much energy to break it, Whereas weak bonds have high chemical energy, as they can be easily broken to harness whatever energy is within the bond. Weak bonds are more utilizable. It's like the chemical energy, you can't actually use it unless you can break it. And if you can't break it, you can't use it. But if you can't break it, you can use it. Let's think about how this relates to polar and non-polar stuff. Because the more polar a bond, the shorter and the stronger. That means it is harder to break. That means it has less chemical energy. The more non-polar a bond, the longer it is, which means that it's weaker, and that means that you can easily break it to utilize the energy within, which means that it has more chemical energy. Let's review. So you have an electronegative element, N or O or F. Probably have a polar bond, right? And then you have just C and H's are like the same element. You have a non-polar bond. The electronegativity difference of a polar bond higher. That means you have a shorter bond length. That means that you have a stronger bond, which means that it is more difficult to break the bond, which means that you have a lower chemical energy. You cannot utilize the energy within as well, or as easily. Non-polar bond, lower electronegativity difference, higher bond length, which means that your bond is weaker. And that means that it is less difficult to break the bond. And because of that, it has more chemical energy. You can break the bond easily to utilize the energy within. Compare the chemical energy in the bond over here, this carbon to this oxygen, to the bond from this carbon double bonded to this oxygen. For our double bonded, that would be a ketone. Our bond length is shorter because of that double bond. That means that it's stronger, which means that it is more difficult to break, which means that we have lower chemical energy because it's harder to break and utilize the energy within. C, single bonded to an O, our bond length would be longer, which means that our bond strength is weaker, and that is easier to break, which means that the difficulty is lower, and that means that you can easily break it to utilize the chemical energy within, meaning that we have a higher amount of chemical energy. Some examples. So carbon to an oxygen, that oxygen is very electronegative, NOF, which means we have a polar, which means we have a short bond, which means we have a strong bond, which means we have low chemical energy. CC, same element, which means same electronegativity, which means that it's very nonpolar, long bond, weak bond, high chemical energy, and it's like the same thing, right? And you can read that if you want, but I don't think it will come into play. Let's talk about something which has a ton of chemical energy, and that is adenosine triphosphate. I think it's so fun to say, ATP. So this is our universal energy currency. And remember, anything I have within brackets, do not need to memorize it. So you have your adenosine. Oh, this is a nucleotide, by the way. And then this is the important part. You have 3 negatively charged phosphate groups. That means that each of them have a negative charge on them. There's one phosphate over here, another phosphate over here, one phosphate over here. All of them have negative charges. And what do we know about negatives and positives? Negatives will repel each other, and so, as will positives. So that means that it's very unstable. Like you give it a little bit of energy, bam, a phosphate group will screw off because it was being repelled, and then it's like a rubber band, really tight, and it's off. So that means it has very high chemical energy. It is very easy to break the bonds between the phosphate groups because they destabilize the molecule. They repel each other, which makes for a weaker bond. The third phosphate group can be easily broken to yield energy. So we look over here, adenosine triphosphate, there are 3 phosphate groups, right? So once that third phosphate group is released, it will create an ADP, which is adenosine diphosphate, where tri meant 3 and di means 2. It's ATP with 1 less phosphate group. It's considerably more stable, has less of those repelling negative charges, and a reverse reaction is possible and done universally to create another ATP by adding another phosphate group. So here are the diagrams of them. We have our ATP over here. As you can see, there's a negative charge over here, negative charge over here, negative charge over here, and they're all repelling each other, which means that the third one will easily screw off. Once that happens, you break that bond and energy within it is released. We often use water to provide the initial energy needed to break up ATP. So we add the water that helps break up the bond. We lose a phosphate group, which would be like this one, right? But we also gain the energy within, which can be used to do different things. And this is our ADP. It's like the exact same thing, but it's missing a phosphate group at the end. And it's more stable because it has less repelling negative charges. Okay, so Let's talk about this symbol, which is a
uppercase delta.
and it simply denotes a change in something from initial to final. Our equation is like the delta of x, where the x is anything, is our x value at the end minus our x value initially. And then for the reaction sense, the like you're looking at the change in like I don't know, like the temperature from like the reactants to the products, you would be products, which would be our final, minus our reactants, our initial. And it's not like actually subtracting the products and reactants, is subtracting characteristics that it had when it was in this state. So that would be like temperature, energy, whatnot. This does not depend on anything in between. Only the final and initial value. So you could have something that goes like crazy, like blah, 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 blah. All that matters is the beginning and the end. So if you have a positive delta x value, that means that your amount of x increased going from your initial to your final. If you have a negative delta x value, that means that your value of x decreased going from your initial to your final.
Let's look at an example of a delta function. Let's say that we wanted to know the delta price from April 1st, 2020 to November 27th, 2020. This is our general equation. Our delta x is equal to our value of x at our final state minus our value of x at our initial state. So our final state is here November 27th, 2020, and our initial state is April 1st, 2020. We look at the value at that moment. Our final value was 67.87 USD, and our initial value was 65 USD. Subtract that, you see that our delta P is 2.87 USD. Now, what about everything in between? Like over here, we see that there was a clear peak that was higher than our final price, but this does not matter. Delta is a state function. Nothing in between matters, only your value at the final and your value at the initial. Now, what stock is this? CVS, Pharmacy and Drug. As you can see, it has a clear uptick. To all my hype beasts out there, CVS is the hypest and the beastiest drug store stock that you could buy. And 5 years from now, when you post on Instagram, I just got a Honda Civic 2011, everyone's going to be like, wow, this person made responsible financial decisions.
So let's talk about thermodynamics. We'll start with entropy. Entropy is denoted by the symbol S, and it is a measure of disorder. The more positions possible to be occupied, the more disorder, the higher the S. So there are a couple of relationships you can take from this. You won't be tested on it, but if you have a higher heat, you have higher speeds of particles, which means there's more random movement, more positions possible, more disorder. So you have more S. If you have more particles, you have more positions possible to be occupied and more disorder. Again, this kind of definitional stuff, I don't think you'll really need to know. It might be useful to know a couple of things on this page. So change in entropy, delta S. So our entropy change going from our initial to our final. If you have more positions possible, such as more particles going to a solid to a liquid to a gas, liquid to a gas, you have a positive delta S value. If you have less positions possible, less particles, liquid, solid, gas to solid, gas to liquid, you have a negative delta S value. Your entropy went down. Enthalpy. So basically, the only thing I want you to know is the definition, where enthalpy, or H, is said to be the total energy within something, and delta H is said to be the change in the chemical energy from the reactants to the products. So what we just talked about ties into the laws of thermodynamics. Again, they cover it, but I really don't think it's all that important. So the first law is the conservation of energy. Energy cannot be created, nor can it be destroyed. It can only be transformed. And energy is often conserved in the form of heat. So the implication of this is that a reaction does not create anything new. No new matter is being created, nor is any new energy. The second law is a little more relevant, and is that the entropy in the universe is always increasing. So that's disorder. The implication of that is that reactions that increase entropy are favorable. That means that reactions that have a positive delta S value are favorable. I don't think a lot of this is useful, but it's out there. Now, this is useful. So free energy, or G, is the energy available at a given moment that is able to do work. Remember that work is just some action that is done. If something has no free energy, a G value of 0, it can't do squat. Free energy, G, is needed to drive a reaction. What we focus on often is our delta G value, our change in our free energy. And we'll talk about that very soon. Here's our equation. I believe you're given it, and if you were asked a question, you would plug it in. So delta G is often very important and what we want to know. If our delta G is negative, remember that if you have a negative delta value, that means that our products have less of whatever than our reactants. This means that our products have lower free energy compared to our reactants. That means that our reactants gave off an amount of their free energy and they resulted in the lower energy products. That means that when their energy was lost, some amount of work was done. And the implication of this that's really important is that a negative delta G reaction is spontaneous. What this means is that it is a reaction which does not require a continuous input of energy to work, but it does require initial input to get going. We'll talk about this soon as activation energy. If delta G is positive, free energy was gained going from the reactants to the products. The reaction was non-spontaneous and required a continuous input of energy, and if one stopped supplying energy, the reaction would just stop. What do I mean by spontaneous and non-spontaneous? That means that a spontaneous reaction, after it gets going, it just keeps on going, it keeps on going. It does not require a continuous input of energy. However, a non-spontaneous reaction, if you stop giving it that energy, it'll just stop. An example I can think of is you have a ball at the top of the hill. Now that ball won't move on its own, but after you give that initial push of energy and it starts rolling down the hill, the reaction of rolling down the hill, you do not need to keep on applying force. It's already going, and it'll keep on going, while it's going down. However, you're pushing a ball up a hill. And let's say that you think about the reaction in this context as the ball going up the hill. You're pushing it, you're pushing it. You get out of the way, the ball will just fall back down. It was non-spontaneous. You needed to continue adding that force. So here's an important tidbit I don't want to fit elsewhere, is that spontaneous does not mean that it is a quicker reaction. A spontaneous reaction is not necessarily quicker than a non-spontaneous reaction. The rate of reaction depends on something called activation energy. So a reaction with a negative delta G value is said to be exergonic. Exergonic in that it is losing energy and outputting it to the environment. So negative delta G means you have a loss of free energy, which means that it's spontaneous. We look at this graph over here with energy on the y and reaction coordinate. Reaction coordinate just means like the progress of the reaction. We see that our reactants have more free energy than our products, and our products have less. That means our products lost energy. This is an exergonic reaction. You have a negative delta G value. And an endergonic reaction is one that gains energy. So our reactants over here, we ultimately end up with more energy in our products. This is our delta G value, and it is positive. Our products have more free energy now. So positive delta G is a gain of free energy, and this is non-spontaneous because of that positive delta G value. Now we're going to finally talk about activation energy. So reactions don't just start up. They need some input of initial energy. And then if something's spontaneous, it can be thought of as like an initial push to get things going. So oftentimes this is heat provided by the environment because the heat will heat things up and that will help the reaction get going. In the case of the ball rolling down the hill, it needed that initial push to get going. The initial energy input needed is called activation energy. When you're trying to find the activation energy of one of those graphs that we saw earlier with the energy on the y and the reaction coordinate on the x, the activation energy is the distance of free energy from your reactants to the immediate peak, the next immediate. The lower the activation energy, the faster the reaction. This is important. The higher the activation energy, the slower the reaction. An enzyme is a protein that makes reactions happen or just happen faster. Enzymes can act as biological catalysts and they lowered the activation energy. And if you have a lower activation energy, you have an increased speed of reaction. So catalysts lower activation energy, and they make that hump, like the hump right after the reactants, smaller. And they speed up the reaction, but an extremely important note is that they do not change delta G. So let's take a look at this graph over here. We have a reaction that goes without a catalyst, and we have a reaction that goes with a catalyst. We see that the activation energy with the catalyst was lowered. And this means that this reaction on the bottom dotted line will be the faster reaction. And this one will be the slower reaction. However, remember what delta means. Delta is a state function. The only thing that matters is the value at the final and the value at the initial. All the catalyst did was speed up the reaction. It did not actually modify or give you a different product. So we have the exact same products, we have the same reactants, which means that our delta G was not modified at all. Our delta G for both of these reactions are the same. Nothing in between matters.
So let's talk about coupled reactions. It is why our delta G value is kind of a big deal. So reactions can be paired together. A reaction that releases free energy, which would be a spontaneous exergonic one that has a negative delta G value, can be used to supply a non-spontaneous endergonic reaction, one with a positive delta G value, with the free energy input needed to drive it forward. So in order for a coupled reaction to work, the exergonic reaction must release a sufficient amount of energy for the endergonic reaction to work, which means that the math over here is that our negative delta G value must be greater in magnitude, stronger than our positive delta G value. So that there are three possible relationships. If you pair an endergonic plus an endergonic relationship, they're not coupled. If you have an exergonic plus exergonic relationship, they're not really coupled. But if you have an endergonic with a weaker exergonic reaction, they're also not coupled. Okay, that makes sense. Because over here, because our exergonic reaction is weaker, has a negative delta G value of a lower magnitude than our positive delta G value, is not coupled. So the only possible situation is this one. So earlier we talked about ATP. We talked about how ATP has a lot of chemical energy, and that can be seen in its high negative delta G value. We see that this is a coupled reaction. We're adding an inorganic phosphate to a glucose to form G6P, and that is not spontaneous. That took an input of energy, whereas ATP going from here to here actually gave off free energy. It has a negative delta G value, it's spontaneous. So because this negative delta G value is greater in magnitude than this positive delta G value, this would be a favorable reaction. So let's go over some examples. You might be asked a question in graph form. So let's think first. I wasn't really, I forgot how my animations work. So I added like really cool animations to each one. So if you want, you can pause and you can write which one of these are endergonic and which of these are exergonic. Okay, so A is exergonic, B is endergonic, C is pretty similar, endergonic. And I made the animation really slow so I could build up the suspense. Holy crap. Dude, that took so long. I hated that. That annoyed the crap out of me. All right, let's move on. So our endergonic ones are B and C. We see that over here, over here on the y-axis for all these would be energy, and then over here would be like reaction time. So over here, we're endergonic. We see that we have a positive increase in our G, a positive delta G value. Same goes for C. And for exergonic, we have A and D. So A lost energy, negative delta G value. Over here, our reactants lost energy, negative delta G value as well. So now let's identify the activation energy and delta G values of each one. So yeah. So as you can see, our activation energy is the distance in energy going from our reactants to the next peak. So this is our activation energy for this one. So activation energy for this one, activation energy for this one, activation energy for this one. So let's look at our variable couplings. So think about this yourself and try to figure it out. Okay, let's get to it. So we have this exergonic reaction, meaning that exergonic means it has a negative delta G value, and it gives off this amount of energy that can be used to power another reaction. So let's see if we can power any endergonic reactions. So we have like a value of 2, and endergonic, we have 2 over here. We see that this one needs an input of 1.5, and this one needs an input of like 0.5. So you could pair A with either one of them. Now, let's look at our exergonic reaction over here. We see that while it also has a negative delta G value, that it only gives off about 1 unit of that free energy, which means that it can only power or be paired with non-spontaneous reactions that don't need more energy than it can provide. So if we compare it to B, we see that B only needed half a unit. This one has 1 unit. Our negative delta G value is greater. These can be paired together. And we look over here. This one needs an input of 2 units. This one only has 1. This is not a favorable reaction. You do not have a strong enough delta G value, negative delta G value, to power this one. Huh. Okay. So yeah, those are our variable couplings then. So let's order them from the most negative to the most positive delta G value. We would have A. Oh, A, I'm sorry. A should be the most negative, B less negative, more positive, most positive. And let's order from the smallest to largest activation energies. And we have that B and A are equal, even though they are, one is exergonic and one is endergonic. And then we see that D has a greater activation energy, and C has the largest one. So this would also be ordered from the fastest reaction to the slowest reaction. Because C requires the most energy input, has the highest activation energy, it is the slowest one out of these all. Whereas B and A, you would expect them to be around the same rate because they have the same activation energy. And notice that that both of these are identical, and one is exergonic, one is endergonic. So remember that whether it's endergonic or exergonic does not determine its rate of reaction, only the activation energy. So let's talk about metabolism. Metabolism are the entire set of chemical reactions that convert molecules into other molecules to harness or release energy. So there are 2 types of metabolic reactions. There are anabolic reactions, which build larger molecules from smaller molecules, and they require an input of energy. That means that these have a what kind of sign? Delta G value? A positive delta G value. And that would be non-spontaneous as well. So how I like to remember is that ants build stuff. So you have like a little ant. So a catabolic reaction breaks down molecules into smaller molecules. And breaks down larger molecules into smaller molecules. I'll have to edit that. And in the process, they release energy. This is a exergonic reaction with a negative delta G value. So how I like to remember is that cats knock stuff down, and they generally don't make things, but happiness. Anyway, yeah. Oh, it's just an ant. Hello there, big fella. Bye-bye. Get back here. Get out of here. Actually, get out of here. Give me a goodbye kiss. Mwah. Get out of here. Anyway, so an anabolic reaction builds larger molecules from smaller molecules, and they require an input of energy and spill stuff. As an input of energy is needed, that means our products have more free energy. They gain energy because, an input. And they have a positive delta G value. So you need to know this relationship. If there's an anabolic reaction, they require an input of energy. That means that they are endergonic. Because they're endergonic, that means that they have a positive delta G value. Because of that positive delta G value, that means they're non-spontaneous. So an example of this would be ADP plus inorganic phosphate, where a phosphate is just like literally just a phosphate. It's not attached to anything. To make ATP. This was building a larger molecule out of two things. That is anabolic. And that means that it was so catabolic reactions, which would be breaking down molecules into smaller stuff, and they release energy. That means that our products have lost some amount of energy. We have a negative delta G value. So we have a catabolic reaction. That means we have a release of energy, which means that it's exergonic, which means that it has a negative delta G value, which means it's spontaneous. Over here, we have the reverse reaction of what we saw on the other page, which would be we have ATP, a larger molecule, we break it up into two smaller molecules. That was a catabolic reaction. So let's go over the differences between them. So for a catabolic reaction, are we going from big to small or from small to big? We are going from big to small. A cat will break stuff into smaller little bits. Okay? And then the energy flow, what does that mean? Oh, okay. So, sorry. So because it is catabolic, it releases energy, which means that it releases energy to the external environment. Now, what is the name for this? Exergonic reaction. Easy. And then our delta G value would be a negative delta G value because we were losing energy. And so what? That means that this is a spontaneous reaction. So try it for yourself on the anabolic one. We'll go over it in like a second. So it's actually an anabolic reaction is going from small to big and spilled things, and then they make it bigger. Wow. And the energy flow is that energy is being put into it. So it absorbs energy. What's the name for this? Is endergonic. That means that it has a positive delta G value. So what? That means that it is non-spontaneous. It needs a continuous input of energy. So we talked about coupled reactions before. Let's talk about it in context of catabolic and anabolic reactions. So a catabolic reaction has a negative delta G value. An anabolic reaction needs an input of energy to go. That means there's a positive delta G value. A negative delta G value, a reaction with a negative delta G value can be coupled favorably with a reaction with a positive delta G value as long as it is strong enough to provide said energy. So remember, the reaction needs free energy to go. And anabolic reactions are non-spontaneous and they need a continuous input of energy. Where catabolic reactions are spontaneous and they continuously release that energy, which means that they can power anabolic reactions. A catabolic reaction can release the energy needed for the anabolic reaction. This is called coupling. So a coupled reaction in this context is a catabolic reaction that is used to power an anabolic reaction. It's time for the meme break. All right, let's see what we got. Oh, that's pretty funny. Oh, really funny. Oh man, I should text my mom that.
Hi everyone. Before we started cellular respiration, I thought this would be a good time to take a quick 6-minute break and share with you guys an original song that I wrote. Thank you. I see the trees and all of the bees. I see the pollen in your hair. Cellular respiration. So cellular respiration involves a bunch of redox reactions. And redox reactions involve exchanges of electrons. So oxidation is where a species loses electrons, and reduction is where a species gains electrons. You remember this via oil rig, where oxidation is loss of electrons, and reduction is gain of electrons. I like to remember redox reactions in a biological sense, not exactly by electrons, but in terms of energy. So oxidizing is where energy is being lost. That energy is being released into the environment, and it can be used by other processes to do work. Reducing is taking in energy. It takes in energy,
and then it becomes a higher energy compound, and perhaps that is a form of energy storage, such that you can utilize the energy within later through another oxidation reaction of that. Here is a useful generalization. Catabolic reactions are oxidation reactions, and anabolic reactions are reduction reactions. That means you undergo oxidation to release energy for work, which also means that catabolic reactions release energy for work, where a reduction is a reaction to store energy for future work, which matches up with an anabolic process. So we have two very popular examples over here. We have ADP plus an inorganic phosphate goes to ATP. So if you remember the anabolism, an ant colony will build something. So this is building a larger molecule, ATP, out of two smaller molecules, ADP and an inorganic phosphate. Because this is anabolic, we know that it's reduction. An input of energy was needed over here, and it stores it within ATP, the bonds within ATP, and that ATP can be used later for energy. Now we have the reverse reaction, which is an oxidation reaction. We know it's oxidation because it is a catabolic reaction. Over here we have ATP, adenosine triphosphate. We're converting it into ADP, adenosine diphosphate with only two phosphates, and we're losing a bond to a phosphate group. That means that this is a catabolic reaction. We're going from a larger molecule to a smaller molecule. Because it's catabolic, we also know it's oxidation. Because it is oxidation, it is releasing energy that is available for work. So redox reactions are often paired. For example, an oxidation reaction, when it releases its energy, something will use that energy, which would be a reduction reaction. In the process of something being oxidized, another uses the release energy to be reduced. Here are two examples. You might be asked on your test, like, you have this thing, it gives energy to that, which one was reduced, which one was oxidized? We have NADH, it becomes NAD+. We have a protein that gains the electron from the NADH. In this case, we can use a simple oil rig and think in terms of electrons, where NADH loses high energy electrons, so it was oxidized. Oxidation is a loss of electrons. And then for the protein, it gained an electron. Reduction, rig, is gain of electrons. You might also have something like this, where you have an oxidation reaction and a reduction reaction. Or I guess you wouldn't know that yet, but you have a 6-carbon thing. It undergoes a catabolic reaction. We can see that in that it becomes two smaller things. We're breaking up a larger thing into smaller things. So it's an oxidation reaction, and that releases energy in the process. And on the other hand, we have smaller components that make up a larger one. So this was an anabolic reaction, which means an input of energy was needed. And because you ultimately ended up at this, that means there was indeed an input of energy. So this is reduced. This is reduction. This is oxidation. Here is the generalization you want to know for pairing. A catabolic or an oxidation reaction helps power an anabolic or a reduction reaction. They're paired up together. You break up a carbon-based molecule that can be used to reduce ADP to make ATP, the reduction reaction. So cellular respiration in a nutshell. A series of catabolic and anabolic reactions that convert chemical energy in fuel molecules, glucose, fats, proteins, to easily utilizable energy in the form of ATP. Now, what do I mean by utilizable energy? I mean, well, let's consider how difficult it would be and the complications that would come if we just use the glucose that after our stomach breaks it down, we just have glucose. So glucose is a 6-ring structure. It has carbon-carbon bonds, it has carbon-H bonds, it has carbon-oxygen bonds. A lot of different bonds. And in order to utilize the energy within bonds, you have to break a bond. Processes all over our body need energy. And they get that energy from molecules that store energy and can give it up. But if you had to break every bond in glucose, that would require different machinery, that would make things more complicated, and that is why we convert everything to ATP first. Not everything per se, but for our purposes, everything. So if you remember the structure of ATP, adenosine triphosphate, it has those 3 phosphate groups on them. They're negatively charged, they repel each other, and they're very easy to utilize. So I'll just read this. ATP is easily utilizable for different reactions due to how easy it is to harvest their energy within them, break bonds. Efficiently harvesting all the energy within a glucose would be difficult, as more advanced machinery and specific circumstances would be needed to thoroughly utilize the chemical energy within the bonds. Converting to ATP first is much more efficient. Now, you won't be tested on this per se, but I think that it was useful to go over because it helps show how important cellular respiration is to all organisms. So, what is the flow of energy? As we saw before, we used to have energy in a glucose molecule, and we'll just focus on that for now. And we ultimately ended up with energy in the form of the bonds within ATP. So our glucose is oxidized in the smallest bits. And this is a form of catabolism. It is a catabolic reaction. We start out with that 6-carbon glucose, and all of it ultimately ends up in the form of 6 1-carbon CO2s. That glucose was broken up to a bunch of little bits, catabolism, and that was an oxidation reaction. So we know it's an oxidation reaction, which we know release energy in the process. And we know that redox reactions are often paired with each other. So the energy release from breaking down that glucose is ultimately used to power the reduction of ADP to ATP. This reduction is what gives ATP the energy to drive reactions. This was a conversion of glucose energy into the versatile ATP. I would know the components of the equation. You don't need to know the exact numbers, but know that it involves a glucose, oxygen, you make CO2, you make water, and you make ATP. Here are some terms related to oxygen that will come up. Aerobic means that oxygen is present or that oxygen is needed. Whereas anaerobic means that oxygen is absent or not needed. The entire process of cellular respiration is aerobic. We will soon see that glycolysis is an anaerobic process, but all the steps together need O2 and are aerobic. Here are some important reactions that I will go over. It might be a bit time consuming. So we have ADP plus an inorganic phosphate makes an ATP. This is an anabolic reaction. We created a larger molecule from smaller things. Because it was anabolic, it was a reduction reaction. Our ADP was reduced to ATP, and it needed an input of energy. Going from ATP to ADP plus PI, an inorganic phosphate, that was a catabolic reaction. But going from that larger ATP molecule to 2 smaller ones. And any reaction that needs it is also endergonic. So I don't know if I covered this yet, but a catabolic reaction is generally spontaneous, so it has a negative delta G value, making it exergonic. And an anabolic reaction requires an input of energy, is non-spontaneous, and would have a positive delta G value. Over here, we're going from a carbon thing to a smaller carbon thing plus a CO2, with that CO2 being the carbon that the carbon thing lost. And as we can see, this is going from a larger thing to a smaller thing. So this was a catabolic reaction, meaning that this is an oxidation reaction. So the reason why there's an NADH here is that the NADH was actually a separate reaction. It was ultimately this one over here. Because the carbon was oxidized, it released some amount of energy and allowed the anabolic reduction reaction of NADH to be produced. So NAD+. These are our electron carriers. Over here, our NAD+ is reduced, gains energy to become NADH. NAD+ was reduced. Now, once NADH is reduced, it has energy, and in order to give up that energy, it is oxidized. Oxidation, it loses its energy, and it gives the energy to something else. So NADH goes to 2 smaller things, oxidation. This is also a anabolic reaction, reduction, oxidation reaction, catabolic reaction, oxidation. Same thing goes for our electron carrier FAD and FADH2. Here are some random terms that we'll talk about and will be useful to know. PI, I've referenced that a couple times, is an inorganic phosphate and is a useful component in a lot of things, particularly ATP and ADP. And it is this structure, you don't really need to know that. And it is a floating phosphate group, meaning it's not attached to anything yet. H plus is a hydrogen cation. If you think about what a hydrogen atom is, it is that proton plus that electron. If you get rid of the electron, it's just a proton left. So an H plus ion is a proton. When you have something within brackets over here, that implies molarity. So like kind of like concentration. So if you have a higher bracket X, you have a higher amount of X present. And if you have a lower bracket X, you have a lower amount of X present. A lower pH indicates that there is more H plus present. It's an inverse relationship. So that would mean a higher molarity of H plus. Whereas a higher pH value, because it's an inverse relationship, indicates that there is less H plus present, which would make for a lower concentration of H plus. So GTP, guanosine triphosphate, is something that we'll talk about a little bit, but is basically the same as ATP. It has a guanosine instead of an adenine, and it is treated as such, which would be like the same thing. We talked about this, but we'll cover it again real quickly. NAD plus and FAD are electron carriers. They can take in high energy electrons and store them for later. This process is called reducing an electron carrier. Once they deposit or donate their electrons, they are oxidized, and their electrons that they release will in turn reduce something else. There are 4 stages of complete cellular respiration: glycolysis, pyruvate oxidation, which we call the link reaction, the Krebs cycle, also known as the citric acid cycle, and electron transport chain, often abbreviated to ETC. Here is an overview of cellular respiration, starting from glycolysis. So we have our 6-carbon glucose. It is split and reacted into two molecules identical of 3-carbon pyruvates. During this process, an input of ATP was needed, and an increased amount of ATP and 2 NADHs were produced. We went from 1 glucose, and we had to use a little bit of ATP to gain 2 pyruvate, some extra ATP, and NADH. Now that our glucose is in the form of 2 pyruvates, it can't enter the next step, the Krebs cycle, until it is converted into something else. So the link reaction serves to convert our pyruvates into a molecule called acetyl-CoA, which is 2-carbon. The link reaction links glycolysis in the Krebs cycle. Pyruvate oxidation. The pyruvates were oxidized, CO2 was released, and a bit of NADH was made. 2 pyruvate, 2 acetyl-CoA, CO2, NADH. The Krebs cycle. The point of the Krebs cycle is to produce a lot of electron carriers. It converts acetyl-CoA into a lot of NADH, FADH2 electron carriers using a series of redox reactions, which release CO2, and also a bit of ATP is made. It actually makes the GTP we were talking about earlier, but for our purposes, it's basically the same thing. So we'll talk about this soon. The electron transport chain. All the prior steps barely made any ATP, but they did make quite a lot of electron carriers. And these electron carriers are used in electron transport chain to ultimately produce a lot of ATP. And this is the step where oxygen is finally used. This is a mitochondria. You don't have to know this term Christe, but I would know that it's double membrane. There's an outer membrane, there's an inner membrane, and this is where a lot of the power happens. There's a matrix, the very inside part of it, and there's a space in between, the intermembrane space, and between that, the inner membrane. 1, 2, 3, I would know these in particular. This is important. I might have covered it before, but we're going to talk about oxidation in hydrocarbons. So if you think about it, when we have a carbon thing and it is oxidized to remove CO2, this was a catabolic process, meaning we went from, let's say that we have a 4-carbon thing and we lose a CO2 from it. That means we went from a 4-carbon thing to a 3-carbon thing plus a 1-carbon thing. That is catabolic, larger into smaller, because it's catabolic is oxidation, and oxidation releases energy. So in the purpose of cellular respiration and everything you'll study in this class, once you oxidize or break up that carbon compound, it releases energy. And that energy can be harnessed to do different things. In our case, it is used to reduce that energy is taken up by electron carriers to reduce them, D plus and FAD, into their reduced forms, NADH and FADH2. Our first step is glycolysis, the cleaving of glucose. It converts, the main purpose of it in the entirety of the cellular respiration steps is to convert one glucose into two pyruvate molecules. And the location is within the cytosol. And I'm going to teach you this real quickly because I was always really confused about it. There are two terms that you've probably heard. One is cytosol and the other one is cytoplasm. If you cut open a cell, you'll find that everything is kind of dissolved and kind of liquidy. Even though you can't see them, the organelles like your mitochondria, the nucleus, the ribosomes, they're there. They're just like dissolved within it. And all that within the cell is called the cytoplasm. However, if you look at a diagram, you'll see that there is depicted as there being like open space around the different organelles. That open space is like the actual liquid part of the cytoplasm. The liquid part is the cytosol. So glycolysis occurs in the cytosol. It has an investment phase and a payoff phase, glycolysis. So we have our 6-carbon glucose. We invest 2 ATP to convert it into 2 molecules called pGal. After that, each of our pGals will undergo a reaction to become pyruvate. Over the course of that reaction, each pGal resulted in 2 ATP being made and 1 NADH being made. That means that we resulted from 1 glucose, we resulted in 4 ATP for 2 ATP per pGal and 2 NADH for 1 NADH per pGal. So our net gain is 2 pyruvate, which are 3 carbon molecules, 2 ATP. It is net. We gained 4, but we had to use 2, and 2 NADH. An important note is that glycolysis is completely anaerobic. It occurs without needing O2. Let's break down our reaction over here. We have our glucose molecule, we use some ATP, and out of it we get 3 carbon pyruvates. We get in a larger amount of ATP than we put in, and we get NADH. So we have our investment phase to energize it a little bit, and then our payoff phase is what makes the little bit of ATP and the NADH. Here's a diagram up close. It might be useful to look at it later. The link reaction or pyruvate oxidation. So as in the title, this is the step where pyruvate is oxidized. And it's also called the link reaction because it links the glycolysis to the Krebs cycle. And its location is within the mitochondrial matrix, so the very inner compartment of the mitochondria. Before our glucose derivative, pyruvate, can be accepted into the Krebs cycle, it must first be converted into a 2-carbon compound called acetyl-CoA. Each 3-carbon pyruvate is oxidized. Oxidized and is oftentimes linked to a catabolic reaction. So we lost some kind of aspect of the 3-carbon one, which is the CO2, turning it into our 2-carbon acetyl-CoA. In the process, the release energy is used to make 1 NADH. This is very important understanding, so I'm going to clarify it one more time. Over here, we are going from a 3-carbon pyruvate to a 2-carbon acetyl-CoA. In the process, it turned into acetyl and a CO2. That is breaking it down. That was a catabolic reaction. A catabolic reaction is an oxidation reaction. An oxidation reaction will release energy, and that release energy was used to reduce the electron carrier NAD+ and NADH. So this is our reaction. We go from 1 pyruvate to an acetyl-CoA plus 1 NADH and 1 CO2. This CO2 accounts for all the carbon present. Our pyruvate was 3 carbon. This is only 2 carbon. This is 1 carbon. 2 plus 1 is 3. 3 is equal to 3. What's the equation per glucose molecule? If you remember, during glycolysis, our glucose molecule was split into 2 identical ones, 2 pGals. So everything after that point happens twice. So our equation is from 2 pyruvate we get 2 acetyl-CoA, we get 2 NADH, and we get 2 CO2. Now that our glucose derivative, it is derived from glucose, is in the 2-carbon acetyl-CoA form, it can enter the Krebs cycle, and the location is also within the mitochondrial matrix. The main purpose of the Krebs cycle is to produce electron carriers. As the glucose derivative is oxidized during the Krebs cycle, CO2 is released. That was catabolic, and energy is also released. Using this released energy, a lot of electron carriers are reduced with the hydrocarbons' high energy electrons. A small amount of GTP is also produced. GTP is basically the same as ATP. And it is important to note that the CO2 leaving is directly from the glucose derivative. We'll see this soon, but we'll see this at the end. I'll clarify it. The Krebs cycle does not use O2 as a reactant. CO2 is leaving directly from the glucose derivative, as I said. O2 is not involved. However, it wouldn't happen without it, which we'll talk about soon. FAD and FADH2 is also differs in chemical energy than NAD+ / NADH, and we will see that this has detrimental impacts on the amount of energy they can output. So here's a Krebs cycle. Now that our glucose derivative is in the form of the 2-carbon acetyl-CoA, it enters the Krebs cycle, and it immediately combines with a 4-carbon compound called oxaloacetate to become the 6-carbon citrate or citric acid, the citric acid cycle. From here, our citric acid cycle undergoes a series of steps facilitated by specific enzymes that you won't need to know until your MCAT. As it goes, it is oxidized, or it's a catabolic reaction, oxidation, and it sheds 2 CO2s, which have 2 of its carbons, to finally reach the form of the 4-carbon oxaloacetate again. So generally, we have our 2-carbon acetyl-CoA. I think it's very useful to know the numbers. Combines with our 4-carbon oxaloacetate, becomes a 6-carbon citrate. Our citrate undergoes a series of reactions to ultimately regenerate oxaloacetate. That allows future cycles to continue by regenerating it. And as it went, it did a number of things. It made NADH. It made a FADH2, albeit a little bit less than NADH, and also made some GTP. Let's look at the equation. We have our 2-carbon acetyl-CoA. We add it to the oxaloacetate. Through a series of reactions, we ultimately end up with NADH, FADH2, GTP, and we regenerate our oxaloacetate, allowing for a cycle to continue. So our 2-carbon acetyl-CoA was directly from our glucose thing, but we released 2 CO2. That means that we do not have any more of our original glucose derivative to work with. What should you know? I would know acetyl-CoA 2-carbon, oxaloacetate 4-carbon, citrate 6-carbon, that citrate will ultimately become this one, and that along the way you made NADH, GTP, FADH2. And that you regenerate the oxaloacetate. The electron transport chain. At this point, we have made very little ATP. We only made 2 in glycolysis and 2 in the Krebs cycle. But we have a lot of electron carriers, and they finally come to play. They're used to generate a ton of ATP. So we use our generated electron carriers. We finally use our oxygen, our O2, and make tons of ATP. The location is across and within the inner mitochondrial matrix and is very aerobic. O2 is finally used. There are 2 parts of the electron transport chain, using the high energy electrons from the NADH and the FADH2 to establish a proton gradient across the inner mitochondrial membrane, and using this created proton gradient to synthesize ATPs using ATP synthase, a protein. So our first step, establishing that H+ gradient. Let's first break down this diagram. So this is our inner mitochondrial membrane. Over here we have the intermembrane space, and we have the mitochondrial matrix. It'll be useful to know the different parts of the mitochondria. We have 4 kinds of protein complexes. They're labeled 1 to 4. You don't really need to know any of that. And we also have a distinct protein that doesn't really interact with them per se, called an ATP synthase. So these protein complexes are basically the electron transport chain. They are the ones that take in the electrons and they do stuff with it. And then our ATP synthase is the one that uses the proton gradient that these made. Let me explain that right now. So NADH and FADH2 deposit their high energy electrons into the protein complex. Remember, by doing that, they are becoming oxidized because they are losing energy, and the complex is becoming reduced because they just gained that energy. So it donates the electron to a complex, and this is a high energy electron, and it is oxidized bit by bit. The energy is oxidized in a stepwise fashion by redox centers, which are like little places that serve to help get the energy out of it. And they release small amounts of energy, which are used to pump protons. So think about it this way. We have a high energy electron over here, a bunch of stepwise steps happen, and each time the electron loses a little bit of energy. And as it loses energy, it releases energy to the environment. And these protein complexes, they use that release energy to pump protons from the matrix to the intermembrane space. This establishes a proton concentration gradient, which means that there's an inequality across the membrane, with more in the intermembrane space, H+, and less in the matrix. This gradient means that protons really want to rush from the intermembrane space into the matrix. Generally, things want to equalize, and we have a bunch of protons over here. We have not that much over here. And if you remember anything about membranes, you'll know that H+ is an ion, and ions have basically no permeability across the membrane. It needs help to do that. We learned about something called facilitated diffusion, like an ion channel, which does that. So as that electron went down the chain and it was oxidized a bunch, eventually it runs out of energy. And if we just kept that low energy electron in there, eventually the process would get bogged down, you know? You try to add more electrons, but it just wouldn't fit or something. So something needs to take that useless electron that was all juiced up, doesn't have any more energy, to drive the reaction forward. Now this is where O2 comes into play. When the electron has been completely oxidized, it has no more usable energy, it must go somewhere so the redox centers don't get clogged up. O2 is split in half, which will create two oxygens. Oxygen will accept two useless electrons along with hydrogen to form H2O as a byproduct. This is where O2 is finally used. O2 was not directly used in any other process, and O2 and H2O are linked up, where the oxygen in the O ultimately ends up in the water of the H2O. So that was the first step. We use the high energy electrons from electron carriers to establish a proton gradient. Now, we use that proton gradient to synthesize ATP. Protons want to enter the matrix, but they can't because of the selectively permeable membrane. ATP synthase, an enzyme, allows the protons to pass through it, facilitate it, but it doesn't really do it for free. It uses the energy of the protons rushing through it to rotate. And as it rotates, it grinds free-floating adenosine diphosphate, ADP, an inorganic phosphate, just a free-floating phosphate group, into ATP and releases it into the matrix. I don't really think you'll need to know this particular part. Yeah, and yeah, that's pretty cool, right? So it used the proton gradient, and then it made ATP. So note that ATP synthase does not directly use redox reactions. It just uses the energy from the proton gradient that came from somewhere, we know where it came from, to grind ADP and PI into ATP. But all of these were all mini redox reactions. They were happening. Earlier I mentioned that you might be asking a trivia question on this for fun, that an NADH differs in energy from an FADH2. An NADH actually has more energy to give. So this results in more protons being pumped, which results in more ATP being able to be made from the electron from NADH. So NADH results in more electrons, more ATPs being made compared to FADH2. Here is a summary. And here is a video that I suggest you watch. I really like it. I think it's really useful. So there are two types of ATP production. I'm not even going to cover this. I don't think they'll ask you, but they might ask you this. Oxidation phosphorylation is where you take an ADP plus an inorganic phosphate to an ATP. The phosphate is literally just a lone inorganic phosphate. So it's kind of like other methods of making ATP. You add the phosphate group because the phosphate group was attached to another molecule. In this process, the phosphate is not attached to anything. It was floating around and then it was added directly to an ADP. And oxidation phosphorylation happens in the electron transport chain with ATP synthase. How do other fuel molecules enter cellular respiration? You don't really need to know this in particular, but know that they convert into components that match up with a different step in cellular respiration, and that's how they enter. So you might be asked a question that gives you, okay, a fatty acid is converted into acetyl-CoA. Where does it enter? And knowing that acetyl-CoA is one of the reactants of the Krebs cycle, you would say, oh, fats enter the Krebs cycle. Okay, fermentation. I only talk about it, but I really don't think you'll be tested on it. But they might give you a trivia question, I guess. Fermentation is a process that is used by a cell when oxygen is not present. It allows glycolysis to continue because glycolysis does not need oxygen. Let's go over a summary of the equation. We can make a maximum of 38 ATP from this process. We made a measly 2 ATP from glycolysis, a measly 2 ATP from Krebs, GTP. And we made a maximum of 34 ATP for the electron transport chain. 34 is a theoretical max, but this is basically never seen in practice due to a number of inefficiencies. The proton gradient might be used for other things, energy might be not as efficient, whatnot, but. Now I want to talk about these two. These two are very linked up. We used to have a 6-carbon sugar molecule, glucose, that ultimately ended up in the form of 6 smaller, separate CO2s. This is a catabolic. This was ultimately a catabolic reaction. What happened was our larger molecule was split up into smaller ones. Larger thing to smaller ones, because it was catabolic, it was oxidation. And all these oxidative steps were used to generate NADH, generate FADH2, and do different things. The 6 carbons found in the CO2s directly account for the 6 carbons over here. And I really want to clarify this. So the O2 is linked to the H2O. The O2 was only directly used in the electron transport chain. After the energy of the higher energy electrons donated by NADH and FADH2 are used up in the electron transport chain by the protein complexes, our O2 is split, and the low energy electrons combine with the newly split oxygen and protons floating around to form water as a waste. That was the purpose of O2. And the oxygen that was over here ultimately ended up in the oxygen of the water. And the reason why I want to clarify this so much is that students sometimes get this confused. They see the diagram and think, oh, O2 is linked up with this one, right? Because there are 12 of them and 12 of them. That is not the case. The CO2 over here left directly from our glucose derivative, where our O2 results directly in this one. So earlier I talked about how pyruvate oxidation in the Krebs cycle doesn't use O2, but is technically aerobic, meaning needing O2. And this is because the entire point of these are to produce electron carriers for the electron transport chain. But the electron transport chain needs O2. If there is no O2 present, the electron transport chain will not run. If the electron transport chain does not run, that means that it would be useless for our Krebs cycle to occur because those NADH and the FADH2s wouldn't do anything. So our body has different mechanisms such that it prevents this inefficiency. So no O2 means that the Krebs cycle in the link reaction does not run, even though they don't directly need O2. Here are the simplified equations. And yeah, glycolysis. You have your 6-carbon glucose, you use 2 ATP, you get 2 3-carbon pyruvates, this is your glucose derivative, you get 4 ATP, so a net gain of 2, and you get 2 NADH. Your link reaction, which links glycolysis with the Krebs cycle, for each 3-carbon pyruvate, you convert that into a 2-carbon acetyl CoA. Well, that was a catabolic reaction or an oxidation reaction to get 1 CO2. That energy released from the oxidation catabolic reaction was used to reduce an NAD plus into NADH. Our Krebs cycle, I put the 2 reactions over here that you should know. We had our 2-carbon acetyl CoA, which combined with a 4-carbon oxaloacetate to become a 6-carbon citric acid or citrate to start the cycle. Our 6-carbon citrate undergoes a reaction and ultimately ends up in the form of 4-carbon oxaloacetate, and the 2 carbons lost are accounted for with the 2 CO2. You make a lot of NADH, you make less FADH2, and you make 1 GTP, which is the same as ATP, basically. I put these in brackets over here because while I think they're useful to put in there, you don't need to like directly memorize it. But I would know the amount of carbons. I think that's very helpful. The electron transport chain. All the NADH and FADH2 made in all of these reactions are used along with O2 to generate a lot of ATP, and the O2 ultimately forms the byproduct H2O. Here is a summary of it that you could read later. Oh, okay. So I thought this would be a good break. So I've been feeling really quite down lately, and I thought about my cat, and I searched everywhere, and these were some of the only photos that I could find. And that made me feel kind of sad because he was really wonderful and I loved him very much. My brother and I, back when we were kids, we would, in the summers, Jello would go off and like sleep somewhere and we make it a game to like go find him, you know? And then once we found him, we would touch his nose because we were kids and we thought that, oh, when their nose is dry, that means they're dehydrated, you know, they're going to dry out. So we would get really worried and we kind of like lightly poke his nose until he licked it. And then we'd cheer a little bit because like, oh man, now our cat is rehydrated. And then we would leave him alone because we wanted him to rest. And now I don't, it's been a long time and I don't really remember him that well. And I wish that I had more photos to remember him by. So I was thinking I should probably take more photos of my parents and stuff. Look at that little fella. Oh, papipa.
Are you ready, kids? Ho! Photosynthesis are the series of reactions that harvest or convert unlimited light energy. And unlimited means like the energy from the sun, you know? It's not actually unlimited. It'll run out eventually. But for our temporal lives, it's basically unlimited. Into usable reactants, which are used to synthesize convenient sugars from inorganic carbon. Let's break that down. So, the goal of photosynthesis, is to reduce. So remember, like reduce in this sense means to energize, like put more energy in inorganic carbon, which would be CO2, atmospheric CO2, into easily utilizable sugars that can actually be used. So CO2 doesn't really have any energy on its own. So we use it to make a compound that will allow us to use energy. So this reduction requires the usage of ATP and high energy electrons, which the electron carrier for photosynthesis is NADPH. And ATP and NADPH are themselves reduced, and they need some input of energy. Where does this energy come from? Sunlight. It's sunlight. Or other forms of light, actually. It's like light, you know? So there are 2 categories of reactions generally. There are the light-dependent reactions, which is using light from the sun to energize or reduce the electrons, which will create ATP via oxidative phosphorylation, which, if you remember, means that there's an electron transport chain involved. And then light is again used to re-energize the electrons and give them to electron carrier NAD+ to make NADPH, and which will have high energy electrons. And the Calvin cycle uses this ATP and NADPH to make organic carbon compounds. So here's a chloroplast structure. You should know the stroma over here, and you should know the lumen. And you should also know that this is called the thylakoid membrane. So here are some initial definitions. Photons. A photon is a ray of light. A pigment is a light absorbing molecules. So chlorophylls are a particular kind of pigment, and they best absorb red and blue energy, light energy, and they poorly absorb green energy, and they reflect it, which why chlorophyll in most plants have a green color. So each chlorophyll contains an electron that is able to be excited. So when a chlorophyll is hit by a photon, which a ray of light, its electron is reduced. So its electron gains energy and is said to be in an excited state. This energy can be transferred to neighboring chlorophylls, exciting their electrons and then becoming non-excited itself, which would be the neutral ground state. And yeah. So a photosystem is a protein complex that contains all those chlorophylls along with other pigments. So once its chlorophylls are excited, most of them act as antenna chlorophyll, meaning they pass on the energy or the excited electron state all the way down to a central chlorophyll pair. This chlorophyll present in the photosystem is special, and it is literally called a special pair. It is special in that it's the end of the line for that particular amount of energy in that given photosystem. Once the electron of the pair is excited, it does not excite another electron. It does not give away its energy. What it does is that it completely donates the higher energy electron to something. So that means that it did not donate its energy, it donated its entire electron, which happened to also have that energy with it. So as a photosystem will ultimately donate its electron from the special pair, that electron must be replaced somehow. We will talk about that soon. So an important note that I want you guys to note, is that that each antenna chlorophyll is being temporarily excited and reduced and passes the energy, not the electron. Besides the special pair, a chlorophyll does not lose its electron.
So, how do photosystems work?
Well, my flipper friend, allow me to explain it to you. So this entire thing is a model of a photosystem. Each one of these are a chlorophyll molecule, and every chlorophyll molecule contains a special electron that can be excited. Excited means that it receives an input of energy and it enters a high energy state. It becomes an excited electron. Or it can also be a reduced electron, because reduction would be the gain of energy. So let's say that we're looking at this electron up here, and it gets struck by a ray of light. Now it becomes an excited electron. That electron gained an input of energy and is now excited. So these chlorophylls are very close to each other. What happens is that the energy from this one is passed on to an adjacent chlorophylls electron, exciting it in the process. As you see over here, our old electron is still there, and what was passed on wasn't the electron itself, but only the energy it had. So it gets passed on to other adjacent electrons, pop, 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 until it finally excites an electron within chlorophyll that we call the special pair. Now, the entire goal of the photosystem was to get the energy to excite our location at the special pair. So all of these are acting as what we call antenna chlorophyll, because they are transmitting that energy, acting as an antenna of some sort. So at our special pair, what it passes on is not energy, but the electron itself. And this is the electron in its fully excited state, and it passes it on to something that accepts electrons. But now we see that our special pair of chlorophyll are missing an electron, and that needs to be replaced from somewhere. For chloroplasts, this comes from two sources. The electron can come from water, or the electron might come from another photosystem. So a non-excited electron is passed from over here to our special pair, and now the process can repeat all over again. Input of light, excited electron. Dot, 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 dot. This one's now excited. Now it donates it. And that, alabaster, is how photosystems work. What'd you just say to me? I brought you into this world! And I'm very glad that I did. What? Alright.
The main purpose of the light-dependent reactions are to enable the Calvin cycle, the dark reactions, to occur by producing two necessary components, ATP and NADPH. And it does this with the usage of free and unlimited light energy. So the light-dependent reactions happen across the dilichoid membrane. It uses two photons to accomplish two different tasks. One is making NADPH, and the other one is making ATP. There are two kinds of photosystems involved in photosynthesis. One is called photosystem 2 or PS2, and the other one is called PS1. PS2 should practically be named PS1, but is named PS2. So PS2 actually comes before PS1. Why? Because it was discovered second, even though it's like the first thing in the actual mechanism. So to remember which one comes first, just remember how annoying it is that you have to remember which one comes first and be like, oh, because it's annoying, the PS2 probably comes first, which it does. Okay, so a photon of light hits PS2, and it ultimately excites that pair's electron. So a given chlorophyll is hit with light, is passed down from all the antenna chlorophyll, da, 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 da. The energy finally reaches a special pair's electron and excites that one. So once that happens, the high energy electron within the special pair of photosystem 2 is completely passed to a series of electron carriers that oxidize it bit by bit, releasing energy that's used to pump protons from the stroma to the lumen. This is just like what we saw earlier with the electron transport chain, with like in cellular respiration, where you had like the little oxidation centers and you oxidize it slowly by bit by bit. After our PS2 donates this electron, it has to replace that electron somewhere. And it does that by taking the electron from H2O. So H2O will be split, and then its electrons will be stolen from it. And then O2 will be released into the environment as a mostly a waste. Also, remember that plants, they use ATP too, and they need to utilize their sugars as well. So plants have both mitochondria, cellular respiration, and chloroplasts, photosynthesis. As you know, what is the thing that you need for a full cycle of cellular respiration? That is O2. So cellular respiration only uses about 10% of the O2 produced by photosynthesis. It releases the rest of the 90% into the environment for us to like eat it and stuff. Okay. Anyways, after this mini electron transport chain, the oxidized electron, like the one that was donated, has no energy and is now given to the PS1, the photosystem 1 special pair. And then a photon hits PS1, passes through all the antenna chlorophyll, and it re-excites the electron, which is now located within the PS1 special pair. The PS1 completely passes its high energy electron to NAD+, which it reduces it and turns it to NADPH. So the proton gradient established earlier, going from PS2 to PS1, is used to generate ATP synthase in the same manner. Over here in this equation, the H2O should really be underlined, but you use light energy, H2O, to make NADPH, ATP, and you also release O2 as a waste product. Here is a diagram that I ripped from Khan Academy because I suck. And yeah, it's really useful. Yeah. Here, I want to synthesize it because it can be kind of confusing. We have two photosystems involved with the light reactions. Photosystem 2, photosystem 1. Photosystems will donate their electrons, right? Which means that they need to get the replacement electron from somewhere, right? For photosystem 2, which is essentially photosystem 1, the electron is from H2O, which was split, had its electron taken, and it produces O2 as a waste product. And then this excited electron goes down a mini electron transport chain and is oxidized bit by bit and is used to pump H plus from the stroma to the thylakoid lumen. In that gradient, the proton gradient that was built up is used to generate ATP using ATP synthase. For photosystem 1, which is essentially just photosystem 2, the source of the replacement electron is the oxidized or like used up electron from PS2. After that electron went all the way down as a mini electron transport chain, had no really useful energy, is given to the photosystem 1. A ray of light hits that, energizes that electron. Now it has energy again. And it is given to NAD plus, reducing it to make NADPH. And NADPH and ATP will be used in the dark reactions, also known as the Calvin cycle. The Calvin cycle, also known as the dark reactions. The purpose is to use the NADPH and ATP generated from the light-dependent reactions to make high-energy, utilizable sugars from inorganic CO2s. Inorganic meaning like, it's like CO2, not very useful by itself. Okay, a location in this is within the stroma. Our reactants are NADPH and ATP that we created, and also the CO2. And our products are sugars, in particular a 3-carbon sugar, so not 6-carbon, like glucose, called G3P. And you also get NAD plus and ADP out of it because you use them up. General process goes in 3 steps. Here's a run-on sentence. In order to go from inorganic CO2, which has no utilizable energy, to an energy-rich sugar, first the gas CO2 has to have carbon attached to it, carboxylation. But just by having carbon attached to it, that doesn't necessarily mean that it has energy. So we need to energize them. We use our ATP and our NADPH in order for it to just not be inorganic phosphate and energize it. So this is called reduction. Reduction would be like, putting more energy in. The produced sugar can't just leave and take all its carbon away with it, because then the next cycle couldn't happen. You can't let your G3P that you produce leave every time, because you still need some carbon to make your initial base. So after a couple of cycles, once you make enough, then you can release what you can, and then the cycle will continue. It's kind of confusing. Oof. Oh, that was very run-on. That was like a run-on sentence. Okay. So carboxylation, which is our making of our carbon base. So CO2 enters a cycle, and it is added to a molecule, which is a 5-carbon molecule called RUBP. And the enzyme that does this is called Rubisco. Some professors mention it. I don't think you'll need to know it. Our now 6-carbon compound immediately breaks down into 2 identical 3-carbon compounds called 3-PGA. That's all that happened here. Carboxylation, which is adding another carbon on. As we see, we did not oxidize anything to reduce it. No energy was input into it. 3-PGA is not useful for direct energy. Rubisco added more carbon, but did not do any reducing. So now you got to reduce each of the 3-PGAs that you made. And you use that using ATP and the NADPH. After you reduce it, you make what we want, which is the 3-carbon sugar called G3P. Because we use the ATP and the NADPH, which had energy, we oxidize them, and then we reduce the 3-PGA. The new created carbon thing now has energy in it that can be utilized. So G3P is our end product, and it can exit the chloroplast to form larger sugars, like glucose, cellulose, or even starch. So yeah. Cool beans. Regeneration. I do not have a diagram. So RUBP, which was the 5-carbon thing that we added onto CO2 in the carboxylation step, must be regenerated to complete the cycle, or continue a cycle, or continue future cycles. So a lot of G3P is needed to do this. Essentially, just remember that 3 cycles are needed to release 1 G3P. G3P is a 3-carbon thing. If you wanted to make glucose, you would combine 2 of the 3-carbon ones to make the 6-carbon glucose. Bammo.
Let's summarize the photosynthesis process. We had our light-dependent reactions, which use the light energy to ultimately create the components needed for the Calvin cycle, or the dark independent reactions. So using the electrons from H2O and releasing O2 as a byproduct, this electron was passed to PS2, where after getting energized, was passed through an electron transport chain, which was used to pump a proton gradient. After that electron was all used up, it was given to photosystem 1, where it was energized again, and then that energized electron was given to an NADP plus to reduce it and make NADPH. The proton gradient that we generated going from the proton gradient that we generated going from PS2 to PS1 was used to generate ATP using ATP synthase. Now that we had those two components, we can enter the Calvin cycle. CO2 is carboxylated to a 5-carbon compound called RUBP to make a 6-carbon thing that splits in half into 2 3-carbon things with no energy. After that, we actually use the components ATP and NADPH from the light-dependent reactions to actually reduce or add energy to these things. And that results in a useful sugar being made, G3P. G3P can be synthesized into larger sugars like glucose. Some G3P is needed to regenerate the carbon-based RUBP to allow the cycle to continue, and multiple cycles are needed to be able to release G3P to do stuff. So let's summarize the equation like we did for cellular respiration. Over here, H2O is involved with light energy, and H2O ultimately releases O2 as a byproduct. H2O provides the electrons needed to drive the light reactions, and to utilize the electrons, H2O had to be split, which produced O2 as a waste product. Light energy was used for these electrons to energize them and drive the production of ATP and NADPH for the Calvin cycle. These three are linked together, or at least H2O and O2 are very linked. Next, we have CO2 with sugars. CO2 is used as a building block to ultimately make our sugars. So inorganic CO2 from the atmosphere is stuck onto another carbon thing and energized, that was our reduction phase, to make useful energy in the form of sugars, G3P, and this reduction was conducted using ATP and the NADPH made in the light reactions. An important note is that this O2 did not come from this CO2. This O2 came from the H2O. The CO2 was used to make the sugars. So some general stuff. And there are 2 statements that I want you to note and understand from this. The first of which is all carbon within biological systems are the result of photosynthesis of plants. Before, that carbon was floating around in the atmosphere, wasn't very useful. It had to be fixated, it had to be reduced by plants through photosynthesis. With the help of H2O, the light reactions use the unlimited energy of the sun to create ATP and NADH. In the process, the light reactions release O2. The dark reactions, the Calvin cycle, use both of these products as reactants, ATP and NADPH, to turn inorganic CO2 into usable energy. Now, plants, they use both photosynthesis and cellular respiration. A byproduct of photosynthesis is O2, and cellular respiration needs O2. Lucky for us, plants only use about 10% of their O2 produced from photosynthesis for their own cellular respiration processes. They release the rest, like 90% of it. Plants provide the living with food and oxygen. To everyone, good luck. I hope you all do fantastic. I have an email if you ever want anything at all. I have office hours at that link, and thank you. Warning, the next 3.5 minutes are nothing but tomfoolery. If you dislike me or tomfoolery, I suggest you click away, and good luck on your exam.
Sure about this, Justin?
Give it to me. See, Josh, I told you I could take it.
Vegetarian bagel bites.
Wow.
Hi there.
Yeah.
Cool.
Oh, of us two?
Yeah, I mean, 3 of us.
How? Like a selfie?
I guess so.
Hey!
I finally coded a program that will prove to everyone that I am the ultimate Garfield fan. No. Easy! Ah!
Hey, do you guys want to see a funny joke? There's a snake in my belly button.
Oh, get him out of there!
In action.
I hate you.
What? I sent a message.
So how have you been, man?
A millionaire Mike Kelly. Why don't you try taking away these guns?
Wow. Wow. I will lonely toad. I walk a lonely road. I'm totally all alone. I'm a toad. I'm a toad. Why was I made this way? Dismay. He's like a little bumblebee. Ba, ba, bee, ba.
In your hair. Barry the bee pheasant is a false prophet. It was a pleasure, but the Tom, foolery must end one day. Good luck on your exam.